Screencast-O-Matic. So we're now recording. Let's go from the current slide, and in a while the projector will finally wake up and do its thing. Okay, a couple of announcements, and here's Skylar. And, Johnson, yeah, I'm trying to remember your first name, though. Yeah. And Cameron. Okay. All right. I think we finally broke double digits. Good. Okay. Announcements. It's not a major one, but just in case, I don't want you to make an extra trip or waste any time. Normally on Fridays, I have office hours on the Birmingham West campus, and Tegan is here, from 8 to 12, okay? This Friday, however, I do have an infusion, so I will not be on campus, either campus at all. My infusion, I haven't figured out what time it starts yet. I think it's around 8, and it goes well into the afternoon, so I won't be there. Huh? Z, got it. I'm sorry, I can't hear. Okay. All right. Anyone else come in since I called roll I didn't catch? Okay. So, I won't be on campus at all on Friday, so don't try to come see me. Don't try to call. I won't be on either campus on Friday. And usually, when I'm there in the waiting room or waiting for whatever, I try to get some grading done. So I'm going to try to whittle down this stack that's growing daily. And I'm still working on spring and summer schedules. The spring schedule was such a terrible mess, and I've got most of it straightened out, but I've still got a fair amount of work to do. So when I'm in my office, that's what I'm working on. When I'm home or waiting rooms or stuff, that's when I'm grading papers. I want to finish those schedules so I can get back to maybe ever catch up on the grading. All right. Any questions on anything we've covered so far? All right. We're in Chapter 2, Polynomial and Rational Functions, so far in the polynomial part. 2.1 was mostly quadratic functions, maximum exponent of 2. Section 2.2 was higher order polynomial functions, exponents greater than 2. And now we're going to do in 2.3, well, this is polynomial rational functions, 2.3, polynomial and synthetic division, okay? But before we do synthetic division, let's think about divisions of polynomials in general. I imagine you've done some of these sometime in your past, or maybe not. So let's see if I'm going to give you a division problem, long division, because most of you are so familiar with calculators, you may have forgotten how to do long division. We need to have that skill. So let's do 12. Let me get my pen set up. There it is. Okay. 12 into 619164. Why not? 619164. That's a nice round number. Okay. How would I do that long division? Don't pull out the calculators. How would I do it by hand? Okay. You start with, in just about every other operations in mathematics that I can think of, we start and go right to left. We add right to left, we subtract right to left, we multiply right to left, we divide left to right, okay? So we'll do 12 into 61. That will go 5 times. Then what do we do? Then we multiply. 5 times 12 is 60. Then we do what? We subtract, and you get a 1. Bring down the 9. Very good. 12 will go into 19. You divide again, and that goes 1 time. Then you do what? Multiply. 1 times 12 is 12. Then you subtract, and what do you get? 7 bring down the 1, then you do what? Divide again. 12 will go into 71. How many? 5 times? Okay. Okay, and 5 times 12 is 60. And then you subtract again, and that gives you 11. Bring down the 6. 12 will go into 116. 9 times, you say? And 12 times 9 is 108. And then you subtract again, and that gives you 8. Bring down the 4. Divide again. 12 will go into 84 7 times. Okay? 7 times 12. Yeah, wait. I shouldn't have done that. I should not have overridden what you said. Students are always right, aren't they? That's what, no, that's not. It's customers are all right. But let's do 6. Okay? 6 times 12 is 72. Subtract. What you get? 12. Okay, here's Reggie. All right. At this point, alarms go off. Ding, 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 ding. Warning, warning. What's wrong? Your remainder is equal to or greater than your divisor. Can't have that. Remember? And that's what sets off the alarms, right? If the remainder is greater than the divisor, go back and add 1 more. So, sorry I messed up. Okay. Let's take this off and that off and that and add 1 more. And that gives you a 7 up here. 7 times 12 is 84. What does that mean for us? Say again? You're done. Okay, good. When you have 0 remainder, what does that mean? That 12 goes into that an exact number of times. And another way of phrasing that, 12 is a factor of 619,164, which of course you do, but I mean, I just was reviewing that and bringing it to your forefront of your mind. And it will go into exactly that many times, which means that 51,597 is also a factor of 619,164, which of course you do. But the thing is, anytime you have a 0 remainder, that means those are factors. Okay? So hang on to that thought. We'll come back to it later. I'm sorry? Evans, got it. Okay. Good deal. Has anyone else come in while I wasn't looking or paying attention somewhere else? Okay. So, y'all did quite well at remembering how to do long division of numbers. Divide, multiply, subtract, bring down, divide, multiply, subtract, bring down. Yeah. Pretty repetitive process, as most things in math are. Very regular, very ordered. All right. Enough of that. What our objectives here will be to use long division to divide polynomials by other polynomials. That's why we reviewed long division right there. Then we will introduce a synthetic division. Okay, it's been developed by Monsanto. To divide polynomials, but there's only certain polynomials you can use with synthetic division. Okay, if their divisors are of the form x minus k. Now, that's probably easy for you to remember. Here's how I remember it. Okay, I'll say this over and over. If the coefficient is 1 and the exponent is 1, then you can use synthetic division. Okay? If your divisors, coefficient 1, exponent 1, then synthetic division is okay. Anything else, long division is required. Okay? But we haven't even gotten there yet. Then, once we get these tools under our tool belt, we'll use come up with a remainder theorem and a factor theorem and use them to help do some shortcuts. Okay? Now, you might say, why are we doing this? Well, if you remember where we left off, one of the key issues was finding zeros of polynomials. Places where they cross the x-axis. Places where profit equals cost. income equal cost, and you begin making profit. Anything like that, you want that equilibrium point. So that's what we're looking for. Okay? So let's start with long division of polynomials, and you just had a pretty good little review of how you're going to do this. Let's suppose we had a polynomial f of x equals 6x cubed minus 19x squared plus 16x minus 4, and for some reason you happen to know, if you looked at the graph of it or whatever and saw it looks like it went right through 2, 0. Okay? Well, that was pretty lucky for you to graph it and go right through that point. Okay? Now, if x equal 2 is a 0 for that, is another name for it is 2, 0 being your x-intercept for that. Remember, there's 4 different ways you can express that. That also means that, give me the other, at least one of the other two. So we already have noticed that x equal 2 is an x-intercept, 2, 0 is an x-intercept of that, which means that x equal 2 is a 0 for that. Give me 2 other equivalent statements, or at least one. X equal 2 is a 0. What will happen if we subtract 2 from both sides? X minus 2 would be a... Say again? X equal 2 is a 0. X minus 2 would be the... It's in parentheses, by the way. Does that help? What's the F word? Factor of this thing. Okay? If x equal 2 is a 0, 2, 0 is an x-intercept, that means that x minus 2 is a factor of that. Okay? And that's what it says right here. You know that, didn't you know that? X minus 2 is a factor. This means there exists a second-degree polynomial that f of x is equal to x minus 2 times something else, some quotient of x, that, oops, is that what that stands for? That goes into it exact number of times. To find that q of x, you can use long division, illustrated in example 1, and that's exactly what we're going to do. If I can get back around here. All right, let's divide 6x cubed minus 19x squared plus 16x minus 4 by x minus 2. Remind me what goes in the house and what goes out of the house. What goes under the radical? Not radical, under the big long thing. Okay, 6x cubed minus 19x squared plus 16x minus 4. And what goes outside is x minus 2. Time out. Before you attempt a long division of polynomials, one thing you need to check. You might say it's 2 things. The main thing is that your dividend, the thing under the house here, is in descending order of the powers, 3, 2, 1, 0, and everyone's accounted for. If this was an x to the 4th, 6x to the 4th, minus 19x squared, you can't do it this way. You have to string it out here, put a plus 0x cubed, then put the rest of it. You have to account for every term. Okay? Usually it's a good idea to do it with the divisor as well. Not absolutely necessary, but it usually helps to make sure you account for every term. You do have to get them in decreasing order of the power. That's required for both of them. And then if you're missing a term here, put in a 0 for that term. Okay? If you're missing a term there, you may put a 0 in. It's usually helpful, but it's no. Now, where do you think we begin? We go, remember, left to right. So let's start with our x here and do this x into the first term here. So how many times will x go into 6x cubed? A little louder. 6x squared times. Perfect. Then what do you do next? You mark on here. Okay? That's what you do. Okay? Anyone else come in since I called roll? Okay. Okay. And pretty sure it's Alexis, right? Okay. Good deal. Anyone else? Good deal. So after you divide, what do you do next? Multiply. So 6x squared times x is 6x cubed. Good. And then 6x squared times minus 2x, minus 2 is, a little louder, 6x squared times negative 2. Negative 12x squared. And then you do what? Subtract. Now that you have signed numbers here, subtraction is a little maybe more error-prone than when you're just subtracting numbers. Subtracting numbers is pretty easy, okay? Signed numbers, you tend to make some errors, or at least I do anyway, so I shouldn't. So what I like to do is and what's the rule? Change signs and add. I can add usually with fewer mistakes than subtracting. So I'm going to change signs, make that a minus and that a plus, and now add them. And what do these add to? Okay, wait, okay, let's go back. What if you had negative 7 minus 10? Okay, what answer is that? Second? Negative 17, okay, got that one. Okay, negative 7 minus a negative 10. What's that one? Second? Okay, that's where we tend to make our errors, right? So if you change signs of this one and add, then you have positive 3. So that's how I like to subtract sign numbers. Changing sign of the subtrahend, if you remember that word, and then adding. And it, to me, eliminates errors. Okay? So if you add these, ooh, where do you go? There. Okay. If you add these two, they add to 0, which is exactly what we want to happen. And if you add those two, what do you get? Negative what? 7x squared. And then what do you do? Bring down the plus 16x. And then what do we do next? Divide again. Start the process over. Divide again. Okay? And JT's here. All right. Good deal. Yes? Okay. Okay. Yeah. Okay. Remember when we did this, this was 6x cubed and a minus 12x squared. So the thing being subtracted from this, those are the signs we changed. We made that a minus and that a plus. Yeah. The thing being subtracted. The thing you're subtracting from the other, that's what you change sign. Just like over here, we changed the sign of the second number. Leave the first alone. Leave the top alone. Change the signs of the second one, the bottom one. Okay? Now, what do we do after we bring down the 16? Start the process over, which is? Say again? Okay, I can't hear. Okay, yeah, she's dividing. X will go into negative 7x squared. How many times? Negative 7x times. Then you multiply. Negative 7x times x is negative 7x squared. And negative 7x times negative 2 is positive 14x. Okay? Now this one you might be able to subtract without changing signs and adding. Whatever. Okay? You still see these go away, which they've got to. And this becomes a little louder. 2x. Okay, you're subtracting, remember? Okay, if you change signs, let's go back and change signs to add. Make that a plus, and make this the minus, and then add. See, I think it's still a good idea to do that. Okay? And what you get? 2x, and then you do what? Bring down the negative 4. Then you do what? Divide again. X will go into 2x. How many times? Second? Plus 2 times. Okay? And then you do what? Multiply. 2 times x is 2x. And 2 times negative 2 is? Negative 4. Ding, ding, ding. We have a winner. A winner. We have an exact division. And just like we saw, it looked like x equal 2 was a 0. We did see this and see indeed x minus 2 is a factor of that polynomial, and therefore the other factor is the 6x squared minus 7x plus 2. Okay? So this is what it does for us. We divided that by that. But that's only the first part of the problem. It says, and use that result to factor the polynomial completely. Well, just a little bit of review of terms here. This was called our divisor. That was called our dividend. What do we call this? The quotient. Okay? And we have a 0 remainder. Hang on to that thought later. Okay? Now, let me tell you something. In the book, they slide this down and put the terms over each other. I don't care. Since I'm doing this and this, I like to put it above it. They like to move it down one. That doesn't matter. But that's your quotient. But guess what the degree of this quotient is? 2, which means what? Say, what do we name a second degree polynomial? Section 2.1. Oh, how soon we forget? What do we name those? Quadratic. And what do we do to factor, to factor the rest of the polynomial completely? We see if we can factor it. And if we can't factor it, what can we always use? Quadratic formula. Perfect. Okay? So let's first see if we can factor this baby. I'm going to erase this little scratch I have here. Okay, or I'll itch at one. I don't know which. Okay. All right. Now, let's see if we can factor 6x squared minus 7x plus 2. Okay? And here's... Got to find you. I know you're in here. Quit hiding. Bertram. There you are. Okay. All right. Now, you got 2 techniques, at least 3, possibly, for factoring a polynomial like that, a quadratic one. We can do it by trial and error, or we can use the quadratic formula, but factoring it, there's one other technique we could use. What initials go before Delco? Anyone know? Y'all aren't mechanics, are you? AC. Remember that? AC method? Long time ago. Lifetimes ago. Okay? But, you think we can do it trial and error? What you think? Let's try it trial and error. Okay? Oh, get back here. Okay. Now, what's one possible factorization for 6x squared? You want 1x times 6x. Okay? That's one. Where do we look next? Sign of the last term is positive. That means those two signs have to be the same, and in this case negative because the middle is negative. Okay? Minus, minus. Now, what's the only factorization for 2? 2 and 1? Okay? We'll try it. Okay? We test to see if this is right by FOILing. X times 6x is 6x squared. That works. Okay? Then we have a minus x minus 12x. I think we can stop right there, can't we? Wrong answer. Negative 13x. We got a negative 7x. So we got the wrong number. So I'd say let's change numbers. Now we can either swap the 2 and the 1, or we could change from x. We could swap 6 and x, or we could pick different ones for the x. Which you want to do? You tell me. Which ones? 2 and the 1. Okay, we'll do that. Okay, we'll take away our smiley face because we're not smiling anymore. Okay, we got it wrong. Okay, so we want to put the 1 here and the 2 there. Okay, I'm going to nix that in the bud. Okay, and here's why. Notice here, do you have any common factors here? What? 2. Was 2 a common factor here? No. So 2 can't be a factor down here if it's not 1 up here. So that one's out of the question. Sorry about that. No smiles again. Okay? So since that didn't work, you almost have to go back. Well, you don't have to. Let's just leave that alone for now. It could be a 1 there and a 2 elsewhere, but let's see. Okay? So you got 2 other Alexiuses here. All right. Now, 2 possibilities to do here. Either swap the 6 and the 1, or, wow, I got that one. Okay, or break them up. Second? 3 and 2. Okay, I heard a 3 and a 2 come up. Okay? So, I need to do my eraser first. Okay? I need to get rid of that. Let me go and get rid of that one too. Okay? So, I'm not going to put the 2 over here. Guess why? Because that's a common factor again. So, I'm going to put the 2 here and the 3 there. Is that okay? All right, let's try that one and see if it works. Check it by foiling. 2x times 3x is 6x squared. We got that one right. Now do the outer, and what do you get? Oh, goodness gracious, where are you going here? Okay. All right. Minus 2x, and then the innards are, whoa, I did that wrong, didn't I? It's minus 4x. Who told me to, huh? I think it was Christian. Okay. All right. Okay. That would be a minus. Goodness, what's wrong with this thing? There we go. Minus 4x. Quit! Okay. And then minus 3x. Finally, we got that far. And then a plus 2. And does that seem to work? Yes, it does. Minus 4 minus 3 is minus 7x. Yes, now we are truly smiling. Okay. So we have our complete factorization. What is the complete factorization of this polynomial? A little louder. I heard a 2x minus 1. 2x minus 1, that's part. 3x minus 2. But we have another part, don't we? X minus 2. The one we divided in originally. Yes, that's the complete factorization of that big old polynomial. Guess what? We now have at least a tool to help us factor cubic polynomials. Before this, the only way we had to factor cubic polynomials if there's a sum or the difference of 2 perfect cubes. That's all we had. Now with synthetic division, we might be able to come up with some other things. That's, of course, if they tell us one of the factors to begin with. Then we're happy because we can divide, we make sure it's a factor, and then use our quadratic techniques. But later, we'll learn how to find those on our own, so we don't have to depend on them telling us. Okay, any questions on this? Okay, I'm going to erase it unless, you got it? Anyone need it any longer? Okay, and let's see how they do it. Well, they tell you how to think. Okay, multiply, subtract, think. Okay, you write this on the outside, that on the inside, just like we did. Now they scoop things down, that's perfectly okay. X, we do X, you think X going into 6x cubed is 6x squared. See, they put it way down there just to have it lined up. So 6x squared, then you multiply. 6x squared times x is 6x cubed. 6x squared times minus 2 is minus 12x. Then you subtract. Now, they don't do the changing signs and adding. Good luck with that, but I like to still think that. Change that to a minus, that adds a 0. Change that to a plus, that adds to a negative 7x squared. Then we bring down the plus 16x. Okay? They don't say that, but you do it. Okay? Now you start it over again. X will go into negative 7x squared. Think that would be negative 7x. That's what they tell you to do. Okay? Once you got negative 7x, you multiply again. Negative 7x times x is negative 7x squared. Negative 7x times a minus 2 is positive 14x. Watch those signs. They'll reach out there and trip you. Okay, then we subtract again, or change signs and add. Changing that sign to a negative, that goes to 0. Change that to that to a positive, that goes to 0. Change that to a negative, and you get a plus 2x. Bring down the minus 4. Think again. X will go to 2x plus 2 times. Okay? You understand? Okay? And then after you do 2 times x is 2x, and 2 times minus 2 is minus 4, and you wind up with a 0 remainder. What does the 0 remainder tell you? They are factors of each other. Okay, you have nothing left over. They go in exactly, so they are factors of each other. This is a factor of that, which means this is also a factor of that. Okay? Now, what we're going to do next is that does the log division. Now, the second part says complete the factorization. So what we're going to try to do there is factor the quadratic part, and sure enough, they just did it like that. Okay, they didn't show you how they did it. They just said this is how it factors. Okay, and that's exactly what we got. Now, the question is, can you come up with 2 more zeros? Since we came up with 2 more factors, can you come up with 2 more zeros? How? We already know x equal 2 is a 0. Okay, so each of these equals 0. 2x minus 1 equals 0. What would that give us? X equals 1/2. Okay, what he did was add 1 to both sides, divide by 2. I told you that's what you did, right? Next one. Set it equals 0. 3x minus 2 equals 0. And what does that give you? X equals 2/3. What he did, believe it or not, was add 2 to both sides and then divide by 3. Now, let's go back for a moment. Flashback in time. Look at this. There were 2 more zeros up there. They were awfully close, and one of them was at 1/2, and one of them at 2/3. Look at that. We found all 3 zeros. I couldn't have picked that out off the graph. I would have said, ooh, what number is that? Or that. Or even though they're the same, I don't know. That was easy to pick off, fortunately. Okay? But the other 2 weren't. But then when we found what the other 2 were, we can easily believe that is x equal 1/2 and x equal 2/3. Make sense? All right. Any questions on that? All right. That was no extra charge. That wasn't done in the book, by the way. Okay? But we will be coming back and doing that later. There is a checkpoint at the bottom of page 136, and please do those as soon as you can after class. If you run into problems, audio-video solutions in both English and Spanish are available at larsonprecalculus.com. No password required, nothing, no codes, anything else. You can just go there and get all the help you want with those with that checkpoint. Okay. In that example 1, we happen to know x minus 2 was a factor of the polynomial because x equal 2 seemed to be a 0 of that polynomial. The log division process produced the remainder of 0, so therefore that confirmed that x minus 2 was indeed a factor. Often the long division will produce a non-zero remainder. And in that case, not a factor. Okay? But it does go into it. So are those all lost causes? It'll turn out no, but we haven't figured out what good they are yet. But let's do one, and they show us way too much here. So let's go back and do it here. Let me see what that was. The wrong pen. Okay, x plus 1 into x squared plus 3x plus 5. Okay, normally we wouldn't do long division on quadratic, but we're going to this time. How would we do that? What would be our first step? Help me. X into x squared, x times, then you do what? Multiply, and that gives you x squared. A little louder. And you get plus x. Okay? Then you change signs and subtract, so that becomes a minus. The other one becomes a minus. Okay? And then you add. And what does that give you? 2x. Then you do what? Bring down the plus 5. And then you do what? Divide. X will go into 2x. Plus 2 times. And then you multiply. 2 times x is 2x. And 2 times 1 is plus 2. No remainder. Well, I mean, it isn't an exact, not a factor. So what's your remainder? You can change signs and add if you want to, or just subtract, then you get a 3. Remainder of 3. Okay. Now, later, we will know the importance of that 3, what that 3 means. Right now, it just seems like, well, not a factor. It doesn't go in evenly. X minus 1 is not a factor. X minus 2 is not a, or x plus 2 is not a factor. So we just have a remainder. All right. Now, there's 2 ways to write that result, and we'll get to that in a minute. Let's see how they did. They did it the same way we did, except they moved everything over to put x's over x's, which, if you like to do it, fine. There's nothing wrong with it. X will go to x squared, x times, putting it over there. X times x is x squared, x times 1 is x. Then they just said subtract, but I like to change signs and add. That becomes a minus, that goes to 0, that becomes a minus, that goes to 2x. Bring down the 5. Divide x into 2x, and you get plus 2 times. 2 times x is 2x, 2 times 1 is 2. Either subtract or change signs and add. Minus makes that a 0. Minus makes this a plus 3. Okay, there's your remainder. Now, how do we write that answer? Here are 2 ways to write it. Okay? You can either write it this way. If you were doing this, you could have written it originally like this. X squared plus 3x plus 5 divided by x plus 1 equals x plus 2, that's your quotient, plus, now how do we used to do that in grammar school? We should have done one otherwise. How do we deal with that remainder? We put R3, that's how we did most of the time. Later we may have gotten a little more sophisticated and did what? Yeah, well, not improper, it better be a proper fraction, okay? And you put that over your divisor. We do the same thing here. Plus 3 over x plus 1. That's one way you can write it. You take the remainder and put it up here over your divisor, the fractional form. The other way you could have done it was this way. X squared plus 3x plus 5 divided by, put that division sign here, x plus 1, and if you want to, you can put it in parentheses just so it makes it easier to see, is equal to x plus 2 let's see, how do they write that? Plus, let's see, that's not right. That's sort of doing the same thing. All right, here's, break this stalemate here. Ashley's here. Okay. Let's go to the division algorithm. Yeah, they'll list both ways here. Okay? I'm sorry. They didn't do divided by, they just went on and multiplied. Okay? So either write it this way, like I said, dividend divided by divisor is equal to your quotient plus the remainder over your divisor. That's one way to do it. Or you can multiply everything on both sides by your divisor. Since it's in the denominator here and the denominator there, it's only the denominator you got, and that will make it x squared plus 3x plus 5 is equal to this thing times that plus 3. Because when you multiply by this, that goes away, you just have a plus 3. And that's exactly how we used to check long division, didn't we? Multiply the divisor by the quotient, and if you had a remainder, then add the remainder. So both of these illustrate what we call the division algorithm. Either write your division this way, or once you have it written this way, multiply both sides by your denominator, and you get this equal the product of those two plus the remainder. Yeah. All right? Make sense? Either way you want to write your result is fine. I don't care. Most of the time the book will leave it in that kind of a form. Doesn't have to be, but it usually does. Okay? Now, there they said it again. They just said the division algorithm. Here they say it again. If f of x and d of x are polynomials. Now, why didn't they name the dividend d of x? Because they'd already named the divisor d of x. You use the same first letter. So your dividend is now going to be your f of x. So if f of x is a polynomial, and d of x happens to be your divising polynomial, such that d of x cannot be 0. Ooh, we didn't mention that, did we? Because you can never divide by 0, right? If that was a number, you see, oh, that's 0, you can't do that. But if it's a binomial or any polynomial, you don't always know. So you have to say that it can never be 0. Then the result of that, here's the other thing. The degree of d has to be less than the degree of f. Sort of the same thing you were saying. It has to be a if the degree is less, then if you put this over that, that would be a proper fractional form. But actually we're doing it the other way, doing this into that. So this has to be lower degree than that, or else you can't divide. It's already proper if the degree of this is greater than that, or even equal to it. I mean, it's not less than that, then it's, degree of that has to be less than the degree of that. If you are, it's improper, and then you can divide. If this was greater than that, it's proper, and you can't divide at all, like 7/12. You can't divide that, okay? That's already there, okay? Now, so d of x has to be less than, and it says or equal than the degree of f, because if it's equal to, you can still divide. Then there exists a unique polynomials, q of x and r of x, q of x being cleverly named as the quotient of x, and r of x is the remainder of x. See, that can have an x in it too. All the ones we've done so far have just had numbers in them, but it could be an x in there as well. Okay, so that's the dividend, f of x, equal the product of the divisor times the quotient, then multiply the remainder. Just like that second form of your division algorithm. Now, if that r of x is equal to 0, then these two are factors of each other. Or, if r of x is the degree less than the degree of d of x, or r of x has to be degree less than that. Remember when we subtracted their numbers and we came out equal to or greater than, you went back and divided again. That's what you keep doing. If this r of x is degree equal to or greater than d of x, it's not a remainder. You keep dividing until the r of x is less than the degree of d of x. Okay? Then if the remainder is 0, then d divides evenly into f of x and is a factor. If that r of x is a 0, then those two are factors. All right. I think we beat that to death, didn't we? Okay. So, here's the other way to write that division algorithm. As I said, two ways. Either on one line, when you multiply through by d of x, or with d of x in the denominator here. Both of those are equivalent. In the division algorithm, the rational expression f of x divided by d of x has to be improper, because the degree of x has to be greater than or equal to the degree of f of x has to be greater than or equal to the degree of d of x. Can't talk about it. On the other hand, the rational expression r of x over d of x must be proper. If it's not, keep dividing. Okay? You don't stop if that r of x over d of x is improper, equal to or less than the degree of d of x. Okay? Good deal. Any questions on that? Blah, 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 huh? Okay. Now, a couple more things. And this is what I said at the beginning. They're getting around to saying it now. Before you apply the division algorithm, or the other way is divide polynomials, follow these steps. Write the dividend and the divisor in descending powers of the variable. If it's not, you're going to get so screwed up and wrong answers. You've got to have them in descending powers of the variable. Secondly, insert placeholders with zero coefficients for any missing powers of the variable. If you don't do that, the odds are you're going to mess up again. So be sure you put in a placeholder for every power of x, integral power of x. Okay? That feels like that's going to lead to another example. Let's see if it does. No, it doesn't. Well, it does in the book. They skip the hard ones in the book and just give you the easy ones. All right? So let's go back and do example 2. Goodness. Finally found white space enough to do example 2. Divide x cubed minus 1 by x minus 1. Okay? And check the result. Okay? When you're doing long division algorithm, what goes where? Here's a house. What goes out, what goes in? X minus 1 goes out of the house. Perfect. What goes in the house? A little louder. X cubed. I can't hear well. What are we missing? Say again? Yes, we got to have a plus 0x squared. What did we just add? Nothing. But we had to put it there. What else do we have to do? Plus is 0x. What do we just add? Nothing. But we had to put it there. Now finally we put a minus 1. You have to account for every term. Remember? Okay. So, now we do what? Start your division. What goes first? Help me. X squared. X, we're going to x cubed, x squared times. Then you do what? Multiply, and that would give you x cubed minus x squared. Now, here's the deal, folks. See, if you had that minus 1 over there, you would be trying to subtract a minus x squared from a minus 1. Those aren't like terms. That's why we put those 0 terms in there. Okay? So, here we can. What do we do now? Change signs and add. Make that a minus, make that a plus, add. That adds to 0. Good. This adds to? Second? X squared. All right, then we do what? Bring down nothing, okay? 0x, okay? But we bring it down. And then what? Divide x into x squared, and that would be plus x, okay? Then we multiply X times X is X squared. Negative X. Okay, then we do what? Change signs and add. Make that a minus, make that a plus, add them. That adds to 0, that adds to X. Bring down the minus 1. Then we do what? Okay, yeah. If you said, oh, that's my remainder. Look at that. Degree of the remainder is equal to the degree of the divisor. Can't happen. Degree of the remainder has to be less than the degree of the divisor. So divide again. X will go into X plus 1 times. And then multiply X minus 1. Ding, ding, ding. We have a perfect factorization. But I thought we knew this, didn't we? Didn't we know that X cubed minus 1 being a difference of two perfect square cubes factors into X, oh, how long? X minus 1 times X squared plus X plus 1, d. That's exactly what we got there, isn't it? So, I didn't really check it. I just said, hey, look at that. We knew that factorization already. We didn't even need to do long division, but it sure worked, didn't it? Okay? So, if we want to check it, remember the division algorithm says you multiply the quotient by the divisor. So let's do it. Okay? Let's check it like they said. X times X squared is X cubed, and X times X is plus X squared, not 2X, multiplying. Okay, X squared, right? And then X times 1 is plus X. Now let's do the second term. Minus X times X squared is minus X squared. Minus 1 times X is minus X. And minus X times plus 1 is minus 1. And when you add those together, cleverly disguised, X cubed, 0 plus 0 minus 1. Yeah, that gives us our dividend. It works, doesn't it? Any questions? Okay, that was example 2. They have a checkpoint there. Do the checkpoint as soon as you can after class, not in another class, but as soon as you can. When you have free time after class, try to do that checkpoint. If you have problems, then go to the website. All right. They also skipped example 3. I have a feeling that's even a bit more involved. So let's take a look and see what example 3 says. Okay? And they do say here, see larsonprecalculus.com for an interactive version of this type of example. Then they're also going to give you help for the checkpoint as well. So let's divide negative 5x squared. Ooh, is that right? Yeah. Minus 2. Ooh, where did it go? Okay. There it is. Minus 2 plus 3x plus 2x fourth plus 4x cubed by 2x minus 3 plus x squared. Okay? How do I write that? Here's the house. What goes in, what goes out? Say again? Yes, you do. You got to get it in descending order of the power. So which are you going to start with, in or out? Out? Okay? Outside the house, what will it be? Say again? The descending order, you start with the x squared term. X squared plus 2x minus 3. Inside the house, 2x to the fourth plus 4x cubed minus 5x squared plus 3x, is that right? Minus 2. All right, did I get all the terms? Yes, okay? So that's the first thing you do anytime you have them mixed up like this. Get both the divisor and the dividend in descending order of the powers. Now we can start, okay? And what would you start with? X squared into how many times? 2x squared times. Perfect. Y'all are good at this. Then what? Multiply, and that gives you 2x to the fourth. Next. A little louder. Plus 4x what? Cubed. Okay. Next. Minus 6x squared, right? Yeah. All right. Then you do what? Change signs and add. Make that a minus, make that a plus, and make the middle one a minus as well. Right there, okay? Now I'm going to add. What do these two add to? 0. These two add to 0. These two add to, second, 1x squared, or just x squared. And then what do we do? Bring down a plus 3x. But since we got rid of 2 terms, let's bring both of the next 2 terms down. Minus 2. Sure, we got rid of the first one, then you'd have brought down 1 term. When you got rid of the first 2, bring down 2 terms. Okay? Now what? Second?
X squared goes in there once.
Okay, it goes in there 1 time. You can move that over if you wanted to. And then you do what? And you get x squared plus 2x minus, get out of there. Oh, wait. It came back. This is confusing me. Okay. Yeah. Okay. Oh, I see what happened too. Okay. No, that's the wrong one. Nope, that's the wrong one. Where are we, Waldo? Okay, go back. There we are. Okay. All right. And then we had a what? Plus 2x minus 3. Okay. And then what do we do? Change signs and add. So that's be a minus, that'd be a plus, and the middle one becomes a minus as well. Yeah, there it goes. And now we add, and what do you have? That goes to 0. This is x plus 1. Okay. Can you go any further? No, because the dividend is lower the degree than the divisor. You're through. So how do we write that? Plus, whoa, get out of there. Remainder, x plus 1 over divisor, x squared plus 2x minus 3. Okay, sort of messy, but there's one expression of your answer. The other, you could string them out and say the dividend is equal to the product of the quotient and the divisor, and then add the x plus 1 at the end. Add the remainder. Okay. And that's for some, oh, they wrote it both ways. Okay. And that's one way they wrote it. Good deal. All right. Any questions on that? All right. Now, let's move on to, if there's no answer, no questions there, let's move on to synthetic division. Now, I actually have had a few students who say they don't like synthetic division. At least the first time or two they see it. But then after a while, everybody loves synthetic division because it makes things shorter and eliminates a little bit of your error, I think. But we'll see. Okay, a nice shortcut for long division of polynomials as long as the divisor is x minus k. Now, they don't always look like that, so here's what I say. I've said it before. Find the variable term. It has to be a binomial, by the way. It has to be. The coefficient has to be 1. The exponent has to be 1. If it's not, you cannot do synthetic division. Okay? So, let's move on. The pattern for synthetic division of a cubic polynomial is summarized this way. Before we get there, I want to point something out to you. Let's go back to that last one we did, or some previous one we did, if it shows up on here. Okay. I didn't do this, but I'll do it now. Now notice one thing we did. Always that first thing that you multiply there, it's going to add to 0 or subtract to 0, right? So why bother writing it down? Okay? Now, here's another thing to note. The x's don't really enter the picture much here, do they? Yeah, you carry them around, but, you know, they'll go. If the main thing you're multiplying and dividing are your exponents. I mean, your coefficients, right? So let's just deal with the coefficients, okay? So let's sort of throw away the x's here and just deal with coefficients. Now, the other thing, remember when we multiply, we always change signs to add. So why don't we just change the sign of that to begin with? And then we multiply and add, multiply and add, multiply and add. Okay? That's the key. That's the key to the synthetic division. Number one, we throw away the variables. We'll bring them back later. You can't just throw them away. But one thing, we just deal with the coefficients. Okay? And secondly, we we change the sign of that k. Always change the sign of the k. And then we just deal with that, like I said. We multiply, add, multiply, add. That's all we do. So here's the technique. You just write for your dividend the coefficients of the dividend. That's all. The A, B, C, and D. Okay? And for the divisor, change the sign of the k. That's all you do. Okay? And then, I have this other stuff that I never read in the book. Skip a line, draw a line. Okay? That's my little phrase. Bring down the A beneath the line. And then from that point on, you multiply add. Multiply k times A, that gives you Ka. Then you add these two. And you multiply k by the result there, put it here, add those two. Multiply k by that result, put it there, add those two. If you wind up with something here, that's your remainder. If you wind up with a 0 there, it went in even. Okay? So the vertical patterns are adding in columns, and the diagonal patterns you're multiplying. I don't usually think it that way, but that's how the book says it. Okay? So let's try it. Okay? Oh, not yet. The algorithm for synthetic division works only for divisors whose coefficient is 1 and exponent is 1 for that leading term. Okay? It has to be a binomial. Now, what if that was a x plus k? Well, you change sign of the k and do it with minus k. So, whichever it is, you do. Minus k is what goes up front. Okay. So, yes?
If you change the sign of the k, do you have to change the signs of everything else?
No, that's what you remember. You change signs and added, right? That's the only thing it's affecting. So that takes care of it, and that's why you always add. Not having to change signs and add, you already changed signs to begin with. Good question. All right. Let's do this one. Is that a candidate for synthetic division? Why? The exponent here is The coefficient is 1, the exponent is 1. Yes, it is. So what goes outside the house? I draw mine a little differently from theirs. A -3. Only numbers. What goes inside where there is no house? Your what goes to the right of that? Where the house would have been if you had a house. And you're homeless? No, okay. What goes there? Okay. Go back here. What goes there are your coefficients of each term. You see? That's what goes there. The A, the B, the C, and the D. Just the coefficients. Okay? So what goes? 1. What's wrong? 0. Again, you have to account for every term. Is that what you were saying before? Yeah. Okay, I thought that might be it. Then, okay, got it? Okay, next, -10, next, -2, next, 4. Got it. Now here's a little trick, or check, I like to call it. What's the degree of this polynomial? Okay, how many terms do we have here? Always one more than the degree, because you have one term that's the 0 thing. So if you don't have that, you're missing a term. And there was a term where we only have 4 up here. We're missing one term. Look for, there it is, the cube. That's why we put in the cube place we put a 0. Just like we did before in long division, only now we don't have to haul around the x cubed, just the 0. Now, what was my little rule? Skip a line, draw a line. Okay? Bring down that first coefficient, 1. And from this point on, it's just repetitive. And what you do? Multiply, that gives you -3. And then you add, -3. Then you multiply, +9. Then you add, and that's -1. Then you multiply, and that's say +3. Then you add, and that's say 1. Then you multiply, and that's say -3. Then you add, and that's a 1. Just a 1, isn't it? Okay. That's your remainder. Okay? So, now is the time we go back and put in our variables. You can't just throw them away for good. You have to go back and put them in. Now, remind me, since this was degree 1, when we divide this into that first term there, what would we get? X, we're going to x fourth. X cubed times. So we start with an x cubed. So this answer is, the quotient is x cubed, you continue, -3x squared minus x plus 1 with a remainder of 1, so I'm going to put it 1 over, and what was our original? X plus 3. Always change that sign back again. Okay? X plus 3. There's your quotient, there's your remainder, there's your divisor. There's your answer. Now, rather do long division? I think not. Okay? This is pretty simple. Once you get it set up, piece of cake. A lot less writing, and you don't have anything you're crossing out. You use every bit of it. And then you put back in your variables at the end. Does that make sense? Okay? That's how we did it. Let's see how they did it. Can I erase this now, or are y'all still writing? Everybody got it? Okay? You should set up the array, they call it, as follows. Notice the 0 is included for that missing x cubed term. Always make sure you account for every term. So on the outside, you put the opposite of this, which becomes a negative 3. And I'm just going to go on and tell you this now. Later, we're going to run into it. Remember, this isn't quite a factor, but if it was a factor to get the 0, which is not going to be a 0 because it has a remainder, you would do x equal negative 3, right? That's what you put outside. Whatever x would equal minus 3. We'll get to that later, but that's just so you can maybe help remember why you changed the sign. Okay? You put the 1, 0, negative 10, negative 2, 4. I always count, make sure I've got one more than the degree. We do, so we're fine. And then bring down the 1. I do the skip a line, draw a line. They don't, but they just do that ugly thing there. Okay? Bring down the 1. Okay? Then you get over here so I can wave my arms around. I don't know how this sounds on the recording because I get far from my microphone. But once you bring down the 1, then you multiply. Negative 3 times 1 is negative 3. Put it up here. Then add. 0 minus 3 is minus 3. Multiply again. Minus 3 times minus 3 is plus 9. Add. That gives you a minus 1. Minus 3 times minus 1 is plus 3. Add, and you get a positive 1. Minus 3 times positive 1 is minus 3. Add, and you get a plus 1. But that's your remainder. I always separate that. Okay? This is your quotient part. And on the quotient part, go in and plug back in your variables, but at 1 degree less than you had there. Why? Because, this was degree 1. Remember, it had to be degree 1. So that reduces it by 1. So x cubed minus 3x squared minus x plus 1 with that as a remainder 1, which you can then write, okay, you can then write just like this. X cubed minus 3x squared minus 1 plus 1 minus x plus 1 plus 1 over x plus 3. Perfect. All right. There is a checkpoint there too. Please do the checkpoint. And we will begin next time with the remainder and the factor theorems. Okay? So, top of the page. Oh, homework exercises. I know you didn't want to leave home without those. Okay, do number 7. Do number 9. They're both at calcjack.com. Then do any of the odds 11 to 23. They're all at calcchat.com. 19's at calcview.com. Then tries. Get started on trying to do sum of 25 to 33. If you run into problems, wait, we'll do some more of those. Okay? Actually, I'd say 25 through 43. Okay? And we'll do the rest later. Good deal. Oh! Do any of you want to take your quiz home? So you have the extra weekend to work on it? Okay. Sorry that some people left. Yeah, if you need to take a quiz, I've got them here. Just because I knew y'all were such eager beavers. Okay. Do you need graph paper? No. Okay. Yeah. Okay. Do you need graph paper? Okay. Do you need graph paper? Okay. All right. What? Need graph paper? Need graph paper? You need graph paper?
Yes.
Okay. Got it? Okay. Need graph paper? Need graph paper? Need graph paper? Okay. Okay. Need graph paper? Need graph paper? No. Okay. Need graph paper? Huh?
I'll take some.
You are, okay. Okay. You go. Need graph paper?
Yes, sir.
Okay. Need graph paper? Need graph paper? Need graph paper? Okay. Need graph paper? Okay. Need graph paper? You got one, right? Okay. Need graph paper? Okay. All right, good deal. Actually, we haven't done all. Number 12 is the only one we haven't done.
See you Tuesday, Mr. Fallon.
Okay, have a good weekend. Thanks.
You too.